Hey guys, welcome back. We'll continue with the book Cracking Codes with Python, and today we're going to learn about two additional ciphers, the multiplication cipher and the affine cipher. Let's get right into it. Let's learn about the multiplicative cipher and the affine cipher. The multiplicative cipher is similar to the Caesar cipher, but it is more secure because it's using multiplication rather than addition. If you want to follow along, you can head over to inventwithpython.com. The link is also in the description down below. Now, in order to understand how the multiplicative cipher works, we need to first cover some modular arithmetic and learn about the greatest common divisor. Now, modular arithmetic refers to math in which numbers wrap around when they reach a particular value. So to visualize that, we could imagine a clock that starts, for example, with a value of 0 and goes all the way up to 11. And if we have a starting value of 0, for instance, and we want to increase that by 3, we would simply go 3 positions to the right from 0 to 3. But what happens if we have a larger number? Let's say we have the number 15. We can see the number 15 is not on here. We will be up here. But now we still have 4 positions left to reach 15. So in that case, we are going to start at 0 again. And we are going to go forward 4 positions. So 1, 2, 3, 4. And again, we end up with the number 3. So modular arithmetic allows us to determine what number is left over once we divided whatever number we have by the numbers that are displayed here on our display. And we can also do that in code. If we open up our interactive shell, we can use the Modulo Operator, which is the %sign. And we could, for example, have a look at what 21 modulo 5 is. So in this case, we would divide whatever number is divisible by 5 and just have a look at what's left over. So we know that 20 is evenly divisible by 5, and then that means that the number 1 is left over. So therefore 21 modulo 5 has a remainder of 1, and that's the result of our modulo operation. We can also use that for larger numbers, of course. So here, for example, we are adding 10 to 200, so we have 210, and then we are performing the modulo operation with a value of 12. So 210 is not evenly divisible by 12, so the question is which number is. And if you were to try that out, we would figure out that 204 is evenly divisible by 12. In fact, if we open the calculator and we divide 204 by 12, we can see that's a value of 17. And then the question is, what is left over? So if we subtract 204 from 210, we get back 6. So therefore, 210 modulo 12 would give us a remainder of 6. Now, if you have a modulo operation of two numbers that are evenly divisible, for example, 10 is divisible by 10, then we would get a modulo of 0, meaning we can divide those numbers without any remainder left over. And the same, of course, is true for any number that is evenly divisible. So for instance, if we have 20 modulo 10, we know that 20 divided by 10 is 2, so it's evenly divisible. Therefore, 20 modulo 10 will also give us a modulo value of 0. So the modulo operation will become quite important when we work with our multiplicative and affine cipher, but we also need to identify the greatest common divisor. And to do that, we need to find the factors of a certain number. So the factors are the numbers that are multiplied in order to get our number. So for instance, let's say we have the number 24. In that case, we could, for example, multiply 4 by 6, and that will give us 24. But there are some other ways we could end up with 24. For example, we could say 8 times 3, that will also give us 24, 12 times 2, or 24 times 1. All of those are going to give us a value 24. And therefore all those numbers we multiplied in order to get 24 are called factors or divisors. So therefore the number 24 would have the following factors: 1, because we were able to multiply 24 times 1, 2, 3, 4, 6, 8, 12, and 24. And each number always has a minimum of 2 factors, the number 1 and the number itself, because any number multiplied by 1 is of course the number itself. But if you only have those 2 factors, 1 and the number itself, then that means the number is not divisible by any other number other than 1 and itself, and it would be a prime number. Let's have a look at another example. Let's take the number 30 and let's have a look at the different factors. So again, we have the number 1, of course, and the number itself, 30. Then we have 2 and 15, because 2 times 15 is 30. 3 times 10 is 30, and 5 times 6 is 30. And so the available factors are 1, 2, 3, 5, 6, 10, 15, and 30. And if we want to find the greatest common divisor between 24 and 30, we would have a look at their respective factors and see which one they have in common that is the largest. So for 24, we had the numbers 1, 2, 3, 4, 6, 8, 12, and 24. And if we have a look and compare the different factors, we can see 24 is not a factor of 30, neither is 12, and neither is 8. But 6 is a common factor or common divisor because 4 times 6 is 24 and 5 times 6 is 30. Therefore, the greatest common divisor of 24 and 30 is the number 6. We are shortly going to write a function that calculates the greatest common divisor for us, and we need to use that for our multiplicative cipher. But before we do that, we are going to learn about multiple assignment, which is a very handy way to assign multiple values in one step. And to do that, we can simply take several variables, for example spam and x. We're going to separate them by a comma, and then we are using the equal sign to assign a value, and then we can assign two values in one step. So here we are writing spam, x equals 42, and then another string called hello. And when we execute that, we are going to assign those two values, 42 and hello, to the respective values on the left side, so spam and x. So if you have a look at the value of spam now, we can see it has indeed a value of 42, and x has a value of hello. Of course, we could have accomplished the same in two separate lines, so we could have written spam equals 42 and x equals hello. That would give us the same result, but we saved a little bit of space because we simply had to write a single line using the multiple assignment statement here. And important to note, we always need to make sure that the number of variables on the left side matches the number of values on the right side, otherwise we're going to get an error in Python. Now the multiple assignment statement is often used to switch two values. So for instance, if we set spam to 42 and x to hello, and we want to switch it around, then we can do that. For that, we would simply write spam, x equals, and then in order to switch those values around, we would type in the respective opposite variable. So spam should have the value of x. So therefore, we're going to write x, and then x should have the value of spam. So therefore, we're going to write that. So effectively, we're writing spam, x equals x, spam. And as we run that, now spam should have a value of hello, and x is going to have a value of 42. And in order to calculate the greatest common divisor, we can write a short program that's based on an algorithm that the mathematician Euclid, who lived 2000 years ago, developed. We don't really have to understand the algorithm, but we need to understand the steps that we take. So here, in order to determine the greatest common divisor of two numbers a and b, we are first checking while a is not equal to 0, we are going to use the following multiple assignment statement. So a and b are going to be assigned to b modulo a and a. That means a is going to be assigned b modulo a, and b is going to be assigned a. And we're going to repeat those steps until a is equal to 0, and then we are going to return the value for b. So to make that more practical, let's have a look at an example. Let's say we want to determine the greatest common divisor of 24 and 32. In that case, 24 would be a and 32 would be b. So 24 initially is not equal to 0. So therefore, we are going to calculate b, 32, modulo a, so 32 modulo 24, which will give us a value of 8. That's going to be assigned to a. So now a has a value of 8, and 24 is going to be assigned to b. So now at the end of the first while loop here, a is going to have a value of 8 and b has a value of 24. Because a has a value of 8 and not 0, we're going to run the loop again. And this time we're going to calculate 24 modulo 8, which of course is 0, because 24 is divisible by 8. And we're going to assign that to a. And then of course, since a is 8, we're going to assign that to b. So now a has a value of 0 and b has a value of 8. Now we check the condition again. Since a is now 0, we stop the while loop and we return the value for b, so 8. So therefore we get back a value of 8. So let's print out the result of that and let's run our program. And indeed we can see we get a value of 8, so that's the greatest common divisor between 24 and 32. So now that we understand modular arithmetic and we also understand the greatest common divisor, we can have a closer look at how the multiplicative and also the affine cipher work. If we think back to the Caesar cipher, we remember that we have this cipher wheel here, where we have a number of different letters and possibly also characters that are always mapped to a certain number. So for instance, the letter A would have a number of 0, then B, an index of 1, and so on and so forth. And with the Caesar cipher, we simply shifted each position by a certain index. For example, if we had a key of 2, we would shift A 2 positions over to C. And the principle for the multiplicative cipher is the same, but rather than adding the numbers, we would multiply them. So let's say, for example, we have the letter E, which has an index of 4, and we have a key of 3. In that case, rather than shifting it by 3 positions over, which would give us the letter H, we are going to multiply that. So we're going to multiply 4 with 3, which gives us the index 12. So that would mean the letter M. And that is how the multiplicative cipher works. And of course, if we end up going over the bounds of our cipher wheel here, we will use the modular operation that we learned about in order to determine the correct value. So we would start going around our cipher wheel again. Now we need to be a little careful though which kind of keys we select, because some keys are going to give us the exact same letter as before. So for example, here we have the original message, and this is the encrypted message using the multiplicative cipher with a key of 11. And we can see, for example, that A has the same value after being encrypted. And we can also see that the letter G is always encrypted to A, and also M is always encrypted to A. So that would mean when we encounter an A in the ciphertext, we wouldn't know which symbol it decrypts to. Does it decrypt to an A, to a G, or to an M? And therefore, when we use the multiplicative cipher, the key and the size of the symbol must be relatively prime to each other. So in our case, for example, we have 66 characters. So that's the symbol set size. And we had a key of 11. Those two are not relative prime to each other. Relative prime means that they are only divisible by 1 and themselves. But in the case of 11 and 66, the greatest common divisor would actually be 11 and not 1. There's also an additional downside to the multiplicative cipher, specifically that A will always encrypt to A, because A has an index of 0, and whatever key we have, 0 multiplied by any number is still going to be 0. So therefore A will always end up being encrypted to A. If you have a key of 5, for example, B with an index of 1 times 5 would have a value of 5, so it would encrypt to F, but A with an index of 0 multiplied by 5 would still be 0, so A would always be encrypted to A, and that's of course less secure. And to fix that, we can use the affine cipher rather than the multiplicative cipher. And the affine cipher basically is adding a second key to perform the Caesar cipher encryption after we use the multiplicative cipher. So that means we would follow the following process. We have our plaintext. Then we would use the multiplicative cipher and multiply by our key, for example, a value of 3. Then we would add a key to it, our key B, for example, 5. And then we would run the modulo operation with the symbol set size. In our example, for example, 66. And that is going to get us the ciphertext. And by using the modular operation on the symbol set size, the affine cipher is much more secure than the multiplicative cipher. So in our example, if we use a modular operation with a value of 66, that means that the affine cipher has 66 times as many possible keys as the multiplicative cipher. So it's much more secure, and we also ensure that the letter A doesn't always encrypt to itself. Now we covered how we can encrypt a message using the affine cipher. We also need to be able to decrypt the message. And in the example of the Caesar cipher, we simply used addition. We went forward in the cipher wheel to encrypt a message, and subtraction, we went back in the cipher wheel to decrypt a message. So that was very straightforward. With the affine cipher, it's a little bit more complicated. Specifically, we need to use the modular inverse of two numbers in order to decrypt a message encrypted with the affine cipher. So specifically, we are going to use this expression where A and M are the two different numbers. So A multiplied by I, which is a modular inverse, modulo M, needs to be equal to 1. And that's because the two numbers need to be relative prime to each other, so therefore we need a modular value of 1. So if we have an example and we set A to 5 and M to 7, then we need to calculate 5 times I modulo 7 is equal to 1. And if we just try this out, we can say if we set I to a value of 1, then this would be 5 times 1, which is 5, modulo 7. 5 is not evenly divisible by 7, and therefore the result would be 5. If we use a number of 2, 5 times 2 is 10. 10 modulo 7, 7 is divisible by 7, we have 3 left over, so therefore the result would be 3. It's still not the value of 1, but if we set I to a value of 3, then we have 5 times 3, so 15. Modulo 7, we know that 14 is evenly divisible by 7 and we have 1 over, so therefore I of 3 would be the correct value. And to go back to our example of the Caesar cipher, in the case of our Caesar cipher, we had a total of 66 keys. So from index 0 all the way up to 65, which is set to the value dot here. So we have 66 values. And if we choose the key of 53 to encrypt our message, then we have the key of 53, which is our value A. And we have a size of 66 for our cipher wheel. So those are the two numbers. And again, we need to find out a value of I so that the greatest common divisor is 1. So therefore, if we try this out, we can see 53 times 1. Since 53 is less than 66, the modulo operation is going to return 53, of course. And if we try that out with 2, 3, and 4, we always see that these are values that are larger than 1. But if we multiply 53 with 5 and run modulo 66 on it, then we get a value of 1 back. And that means 5 is the modular inverse of 53 and 66. And therefore the affine cipher decryption key is a value of 5. And of course we can also express that calculation to find the modular inverse in code. We don't need to understand this, but this is basically how we perform that calculation using a value of A and M, where again A is the key we use to encrypt the message and M is the size of our cipher wheel, so in our example 66. And we're using our greatest common denominator calculation here and then performing these calculations. Again, we don't need to understand that code, but we just need to know that there are ways to calculate that using Python. But one new concept inside of this is this over here. We have two divides by signs right next to each other, and that is the integer division operator. And that basically divides two numbers and rounds down to the nearest integer. So as an example, if we compare regular division, for example, if we divide 41 by 7, we can see we get this value back, 5.857, and so on and so forth. But rather than simply dividing the number, we could also use integer division, and that would divide 41 by 7 and then round down to the nearest integer. So in this case here, we would get back a value of 5 because we are rounding down to the nearest integer. Now we covered quite a bit of math in order to calculate the greatest common divisor and to find the modular inverses. We can write ourselves a helper script, and for that we can create a new file and save this as cryptomath.py, and here we can include the code for greatest common divisor and also to calculate the modular inverse. So here we have our code for the greatest common divisor and to find the modular inverse, and by saving this in a module, the cryptomath module, we can later on import that once we actually write our encryption and decryption code for our multiplicative and affine cipher. Now in order to work with that, we would go ahead and we would import our cryptomath module that we just wrote, and then we can calculate easily, for example, the greatest common divisor for 24 and 32, for example, which is going to give us back a value of 8. And of course we can also find the modular inverse, for example, for the values of 7 and 26, and that's going to give us back a value of 15. So we're going to use that cryptomath module going forward. Now let's have a look at the practice questions. And the first question is, what does the following expression evaluate to? We have first 17 modulo 1000. So we now, whenever we run a modulo operation and the first number is smaller than the second number, then we basically get back the first number, because 17 is not divisible by 1000 evenly. So 17 modulo 1000 is going to be a value of 17. In the second example, 5 modulo 5, we know that 5 is evenly divisible by 5. So therefore 5 modulo 5 is going to be 0. And let's verify that in our interactive shell in idle. If we run 17 modulo 1000, we indeed get back a value of 17, while 5 modulo 5 is going to give us back a value of 0. The next question is, what is the greatest common divisor of 10 and 15? So to do that, we would have to write out all the different factors for the numbers. So for example, 1 and 10 for 10, and also 2 and 5. And for 15, of course, 1 and 15, but also 3 and 5. And then we can see the greatest common divisor, the greatest common factor the two have in common is the number 5. So therefore, the greatest common divisor would be 5. We could, of course, import the cryptomass module to verify that we wrote before, and then run the CGD, so the greatest common divisor function that we specified inside of the module with the values of 10 and 15. And then we indeed see we get back a value of 5. What does the variable spam contain after executing this multiple assignment statement? So spam and x are assigned to hello and world. So here we know that the first value hello will be assigned to spam and the second value world will be assigned to x. So therefore spam is going to have a value of hello. So let's type this out in our interactive shell. Spam, x is equal to hello, world. And if we now have a look at spam, we can indeed see it has a value of hello. The next question, the greatest common divisor of 17 and 31 is 1. Therefore are 17 and 31 relatively prime. And we know that the definition of relative primes is that the two numbers only have a greatest common divisor of 1. So they're not divisible by other numbers, just by 1. And since that's the case, they are relatively prime. Why aren't 6 and 8 relatively prime? So if you have a look at the individual factors or divisors for those numbers, 6 for example is divisible by 1 and 6, but also 2 and 3, and 8 is divisible of course by 1 and 8, but also 2 and 4, so we know the greatest common divisor of 6 and 8 is 2, not 1, and therefore they are not relatively prime. And the final question is, what is the formula for the modular inverse of A mod C? And if you think back, the formula is of course A, the key, multiplied by the modular inverse I, modulo M, the size of the cipher wheel that we're using, and that needs to be equal to 1. We learned about the multiplicative and affine cipher. In the next video, we're going to write a program implementing the affine cipher. If you want to stay up to date, feel free to subscribe to the channel, and see you guys in the next video.